Hi, thanks for being here, everyone. This presentation actually may be a bit different than what you are expecting, in that it is designed to be a bit more of a tutorial describing some of the tips and tricks to use the MATLAB tools that we created and describe in this recent publication here with my co-authors. Its primary use of this video would be if you have some experience using these tools and want a walkthrough of what it is supposed to look like, and it is an abbreviated version of this week-long workshop we ran in December 2020, the course website of which is still available here. Now, a warning here, I'm going to move pretty fast purposely. But the advantage of this video format is that you can pause and rewind, or you can look here to see what part we're on, so it's easy to skip forward to the part that you are interested in seeing, or applying or adapting to your own use. Or, alternatively, play back the video at a slower speed for a more well-paced experience.
And a deeper bass voice.
We're also going to treat it like a cooking show and have each section finish processing quickly. Whereas in real life, some cells actually take a long time to run depending on the length of your data. Now, I want to acknowledge my amazing co-authors on this project, particularly Will Goff, who created a lot of supplemental materials, including this GitHub wiki that lays out step-by-step instructions for a lot of our tools. Now, we're going to be focusing here on this highlighted section here, the creation of usable data from raw biologging accelerometer data. To see a nice talk and some ideas for things that happen later on the analytical end, I encourage you to check out Max Sapansky's talk on a machine learning pipeline for behavioral event detection. Okay, so the goal of this process here today is twofold. To convert raw tag data into a usable format, primarily the pitch roll heading or PRH file that Johnson et al. Popularized in the DTAG data that presents calibrated data in the animal's frame of reference and provides the base data for future research. Our tools include georeferenced pseudotracks, video synchronization information, speed data, a time variable, and cam-on and tag-on indices in addition to typical accelerometer and magnetometer measurements of pitch, roll, and heading. Number two, to present this data in a variety of formats for easy access to your processing tool of choice. This includes portable formats like the PRH file, but also the netCDF files and text files for import into platforms like R, as well as quick look files for ease of sorting your deployments and video files with the data written on top of it for ease of viewing and auditing and analysis. Now, to get ready for this process, you need four things. Number one, code downloaded from GitHub. The folder structure will look like this, with your 5 main scripts here on the outside, and then various subfunctions and modular scripts located in the subfolders. And you'll want to point your MATLAB home function to this folder whenever you start MATLAB. Number two, a MATLAB data table with your data read into it. We provide an import CATS data script for reading the series of CSV files as the output from the CATS software and making a data table that has your data arranged with specific column name headers. You can see this example data on the workshop webpage. Number three, you need a header file. If you don't have videos, all you need is this top information here. But if you do have videos, you may want to mark the tag slips if you have the precise timing of a tag slip. But the most important use here is to help synchronize the data in the videos. We'll go over this section more in step one. Finally, the fourth thing you need is a calibration file. We'll provide some nice descriptions of our calibration procedure on the tag wiki for the way we do it. But the output that you need to run this code is a set of offsets subtracted from the data and multiplicative factors. Now, I get asked all the time, Dave, we didn't calibrate our tag before we put it on an animal, and for whatever reason, the tag is lost. It happens all the time. And as they say, don't panic. Often a tag manufacturer has provided a basic calibration of the data that is either preloaded or can be used to create the offset and factor. There is also, when we get to step 6, a built-in step that performs an in-situ calibration using the animaltags.org tool's spherical cal, which is an important step because the deployment temperatures can often vary from the lab conditions, especially if you're tagging beaked whales or working at the poles, and no one wants their lab in those conditions. In that case, you can create this file such that the factors are 1 and the offsets are 0. However, it's important to know your axis conventions in your tag. In our scripts, we assume a right-handed northeast down orientation. So you'll want to set your factors, acal, magcal, jical, to account for the axis orientations using an ax matrix. Descriptions of how to do this is in the paper and also in the axisconventions.m script. Note, you may notice a magcal on and a magcal off variable. Those are legacy switches meant to calibrate the magnetometer differently from when the camera is off or on. For most tags, including recent CATS tags, those variables can be equivalent now. Step 1 of main CATS PRH tool is the only optional step. It is set up for CATS HD video, but if you don't have this, you may need to create your own movie times file in a different way if you want to precise video and data synchronization throughout the video. If you're just doing data only, you can skip this step, or if you don't want to worry about the synchronization of video and data, you can skip this step and worry about it later. We are working on a 4K implementation, but is not yet ready due to some codec differences and file size issues. So currently this only works with the old CATS HD camera files. The output of this script is firstly WAV files for all audio files that were written onto the movie files or in RAW format. There is a preliminary step using an FFmpeg video script to rip the audio from the videos at high quality. The second output is a movie times file with a viddn, the start number of each video, viddurs, the length of each video in seconds, and a frame times variable that is the time in seconds of each frame of the video from the start of the video. This script is set up to read the embedded timestamps within CATS HD videos, so there may be an offset between frame times from the timestamps and O frame times, the original frame times embedded in the video metadata. But for most cases, these two variables will be the same. While this step is running, which it can take a while, you can set up your header file with the surfacing times to use as synchronization points. You can either use the embedded timestamps or the timestamps from the movie itself, telling the software via this switch in the header file. To use the surfacings as time sync points, the critical thing is to choose beginning and end points with the same definition. For example, the first frame out of the water or the last frame in the water. And the more surfacings you do in each video, the better your synchronization will be. We'll see how this all shakes out in cell 4. Cell 2 here is where you should start if you don't have video data, and it's also where you should start if you ever need to stop and restart the process. Running this cell prompts you to load your mat file with your data in the header file. It will also load, if you've already run this script, or create, if this is the start of the process, an info.mat file that stores the processing information as you go. So you can always restart the process from where you left off if the process gets interrupted. The critical variable to set here is the decfac, the decimation factor you want to use to downsample your data. Set it to 1 if you don't want to downsample at all, but often data is sampled at a higher resolution than you need for most analysis. So for instance, if you collect data at 50 Hz, like we do, you may want to set your decfac to 5 to have final files at 10 Hz. At the beginning of all subsequent cells is some code to check that you have completed prior steps and loads variables from the info file. The workhorse script here is truncate data. When you run this cell, it pops up a time depth profile for you to use to decide if you want to truncate your data file. This just offers the opportunity to cut out data before the tag went on the animal or after it was dislodged, depending on your workflow. Depending on your workflow, you may want to truncate to exactly tag on, like is done for tags that start automatically on deployment, or you may want to keep some data at the beginning or the end. For instance, that could be useful if videos also started before the deployment. The instructions are up top. Press 1 to set the left boundary and press 2 to set the right boundary. You then have to press enter twice to accept the values. As a hack, if you don't want to truncate the data at all, you could just rename your MATLAB file, truncate with the same file but truncate.mat. And then in this cell, it will assume that your file is already truncated as you want it to be. This cell will also prompt you to load your cal file at this stage, and the values are saved in a cal variable for later use. This cell synchronizes your video files with your data using the movie times file you created in step 1 and the header file with the timings of surfacings. The switches at the beginning here are critical to getting this to work for your data. With current CAS data, the timestamps on the video frames are not exactly precise. They can be off by about 0.5 seconds or so. So if precision is important, you'll want to use surfacings or some other metric to calibrate the video with the data. If precision is not important, or if you're watching this in the future when the video and data can be automatically synchronized, you can set this to true. If you don't have video, just set no cam to true. If you have an old version of CATS data where the video and audio files alternate, but you don't have any video data, set audio only to true. If you only have one audio file, you do not need to set this switch. Running this cell, if you don't have video, just create some variables for the workspace. If you do have videos, it brings up a depth profile with your surfacings lined up with the surfacing data. If they don't line up, which can happen if you don't have precise start times on your video, for instance, if you are collecting video from a non-CATS tag, these surfacings will be off, and you can click the surfacing that is supposed to line up with the surfacings you saw in the video. In all cells, a good way to tell what variables are created is to look at the outputs of the workhorse script. So you can always look at the end there to find what variables you need to have created. So if you're trying to do this on your own or use this as a modular script, you don't want to use our own workflow, but want to have the right variables in the workspace, that's how you can kind of know what's supposed to be created. Cell 5. This cell lets you indicate where in your data the tag was on animal so that you can easily limit analysis to this time period later on. Right-clicking zooms in, and left-clicking adjusts the nearest tag slip boundary to the spot where you clicked. Note that if the automatic detection didn't work very well, you may have to do several clicks to move a far boundary closer to where it should be so you don't accidentally move tag on, for instance, when you're meant to move tag off. Cells 6 and 7 start making some of the official variables you'll use in your analysis. Taking the data from the data table, decimating them to be the light length based on your decimation factor, chosen in step 2, and making your tag frame variables AT and MT. In order to make these as accurate as possible, we need to run the in situ calibrations using the animaltags.org spherical calibration procedures. Part of this script running uses a WorldMagM internal MATLAB script to calculate the magnetic field at the deployment location given in your header file. Some versions of MATLAB have trouble running this script, so we run a try catch here that prompts you to look up and input the magnetic field values for your deployment location. This cell then runs a pressure calibration which accounts for temperature and zeroes the pressure. Almost always you want to apply the in situ calibration, but both options are presented so the user can see what is happening. We try to minimize automatic choices so errors are minimized. The input screen gives you some options here, but press 2 to accept the in situ calibration. Cell 7A, called 7.1 in some of the documentation, runs the in situ accelerometer calibrations. What you're looking for in this output graph is that the adjusted values were not over-adjusted, for example, flatlined, and that the median value is in fact better, closer to 1. In this case, all looks good, so we're going to select 2 to use the in situ calibration. Cell 7B does a similar task for the magnetometer, but the calibration was so good in this case, it was within the threshold set such that the in situ calibration was automatically applied. At the beginning of cell 8, you can see some of the modular scripts that are embedded in all this code. ApplyCal takes the raw data as input and applies the in situ calibrations now stored in the cal structure saved in the info file. Cell 8A gives you a first order chance to identify tag slip locations. The bottom plots here are the accelerometer values when your tagged animal is at the surface. For whales, this is usually when it is breathing and thus oriented normally with respect to gravity. What you're looking for are any changes in the long-term average trend. Clicking takes you to a zoomed-in region that allows you to select more precisely the location and duration of a potential tag slip. But it can sometimes be hard to determine at this stage, so it is okay to leave this at a general level, and in the next step, when we calculate animal orientation, the tag slip durations often become more clear. Cell 8B is where the magic happens. Correcting for tag orientation on the animal is a two-part process. Step 1 is identifying periods where the animal is oriented normally with respect to gravity. For us, this is usually when a whale is surfacing, and we select a period of surfacings to make the average orientation during that time period normal. The second period is looking for a spot where the animal is only changing its orientation in the x and the z plane, rotating around that y-axis. While the first change allows us to mathematically orient the tag on top of the animal, it could be oriented in any direction with respect to gravity. So the second stage allows us to rotate the tag so that the x-axis is facing forward. The output, pitch, and roll allows you to check your work and make adjustments if you need to. You can also zoom in next to your tag slips and enter a tag slip adjustment mode, using abrupt changes in pitch, roll, and heading as indicators that the tag changed its orientation. Cell 9 is a chance to run a more robust in situ gyroscope calibration, but this is currently not active. And if you would like to work on this section, please give us a call. Cell 10A and B calculate essentially the noise in the system from which we can estimate animal speed through the water. 10A inputs audio files and outputs a flow noise variable, and 10B inputs a high sample rate accelerometer file and outputs a 4-column jig variable that is the amplitude of tag vibrations, or the jiggle, between 10 and 90 Hertz. Cell 11 regresses these two metrics against orientation-corrected depth rate, so it only really works if you have periods of steep ascents or descents. The graphical interface allows users to look in real time at how choices of threshold affect the data. Generally, the regression will be more accurate if it is restricted to high pitch angles and midwater dives, but overly restricted choices of thresholds may mean you don't have enough data. The final results are plotted so that you can assess the calculated speed against orientation-corrected depth rate, the green and red dots. In cell 12, adjust the note section at the top and the creator note and this information gets stored in an info variable with some metadata about the file creation process. Then this cell creates a basic PRH file. At this stage, there's enough data to do the video processing, but let's go ahead and discuss the next two steps quickly before going to video. In cell 13A, GPS data is added automatically from the CATS format, a POS file with GPS information. If you don't have data formatted in this way, you can actually skip this cell too and go on to 13B. If you have other GPS data from a fast lock system or other observations, you can input that here in an Excel file with time, lat, long, and notes columns. Time is in month, day, year, hour, minute, second format in the same time zone as your data. Be careful since GPS time is often UTC. Cell 13B then imports that data and gives you a map of all GPS data, allowing you to clean up any points that were automatically acquired and appear to be erroneous. After some filtering steps here, gtrack makes a georeference pseudotrack and a KML file. The output maps and KML files allow you to assess your track for quality. Step 13C then saves many of the figures for use in the quick look, makes a track plot file, an NC file, a lat-long CSV file of the georeference pseudotrack, a text file, all with the same data, and then copies the final files to a running PRH folder in your main directory. Cell 14 creates the final quick look file for ease of identifying what deployments were which. You have to choose some files you've already created, including a picture titled ID_name, which could be a fluke image or another ID image, a tag_name, a drone_name if you have one, and then in the QL folder, put an image tagged as map, one tagged as KML, typically a more global view, and any images from the camera you want. This cell also pulls information from the tag guide. Note that for all these, if you want to tag some other random image or a blank image with any of these tags, you could use those as well. Once you've run this last cell, our typical workflow involves moving all the data that now can be used for analysis into its own folder structure, away from the raw data. The last step now is to sync the data in the videos. To do this, run cell 1, selecting the video files you want to stitch data onto, and then directory you want to put the partial files in. It takes about a terabyte of hard drive space for 6 hours of HD video for this stage. These files will be deleted after processing, but you do need that much space up front. And it can take several days to run. After the graphs come up in cell 1 and all looks good, move to cell 2 to start the process of reading 15 seconds of video at a time and stitching the graphs on them. Eventually, you will get a folder full of partial files that then you can use Adobe Media Encoder or some other stitching software to stitch together into your final MP4 file that is a reasonable size, and you can delete then all the partial files. The final videos can be put in your tag data folder and renamed using the rename video script to add the timestamps of the video start onto the video files. Good luck with all this. Feel free to contact me for troubleshooting tips and tricks. Thanks for being here.